Today's video is for physics and AP Physics students, and it covers rotational kinematics with 3 sections. The first will be the symbols and units needed to solve rotational problems. The second part will be linear and angular formulas, and the third part will be additional formulas that you'll need to know. So first we need to get down some name symbols and units. For our names over here, we will have angular position, and that will be given by the symbol theta for a radian. Next, we have angular displacement. And the symbol for that is delta theta, which represents the change in theta or the change in radians. Then we have angular velocity. That's given by the symbol omega, and that would be radians per second. And lastly, we have angular acceleration. And that is given by the symbol alpha, which represents radians per second squared. And now we are going to talk about our linear and angular formulas. For every linear formula, there's going to be a corresponding angular formula that you'll want to know. So on this side, we are going to put our linear formulas, and on this side, we're going to put our angular formulas. So first, for our linear formula, we have distance equals velocity times time. And the corresponding angular formula would be theta equals omega times time. And as you can see here, the position is represented by the theta and the angular velocity is represented by the omega. So we're simply plugging those in for distance and velocity in our linear formula. Our next formula is going to be the final velocity equals the initial velocity plus the acceleration times the time. And that is going to correspond to omega final equals omega initial plus alpha times time. And that's because this represents the final angular velocity, this represents the initial angular velocity, and this represents the angular acceleration, which we're going to plug in for the final velocity, initial velocity, and acceleration in the linear formula. Next, we have final velocity squared equals initial velocity squared plus 2 acceleration times the distance, and that's going to correspond with the formula omega final squared equals omega initial squared plus 2 alpha theta, and that's because we plugged in the angular velocities for the normal velocities and an alpha for angular acceleration for the normal acceleration and the angular position for the normal position. Next, we have distance equals the initial velocity times the time plus 1/2 at squared. And that will correspond to theta equals omega initial times the time plus 1/2 alpha times squared. And that's because we're plugging in the angular position for the linear distance, the angular velocity for the linear velocity and the angular acceleration for the linear acceleration. And lastly, we have distance equals 1/2 the initial velocity plus the final velocity times the time, and that will correspond to theta equals 1/2 omega initial plus omega final times the time, where the theta is going to represent the distance and the two omegas here are going to represent the initial and final velocity in our linear formula. And there's a couple more examples that you guys should know. The linear distance is equal to the angular position times the radius. The linear velocity is going to equal the angular velocity times the radius or distance, and the angular and the linear acceleration is going to equal the angular acceleration times r. And this is kind of our bridge between the linear and the angular formulas and the formulas that ultimately connect them together. There's one more important thing that I'd like you all to remember, and that is when we are moving in the counterclockwise direction in rotational physics, that will be positive. However, when we are moving in the clockwise direction in rotational physics, that is going to be our negative direction.